about hydraulic theory, there's some terminology that I think is important. The word hydraulic is a Greek root hydro, water, and autos, tube and pipe. The original usage of hydraulics goes back to the Greeks and the Romans, where they constructed these interesting cisterns and aqueducts that conveyed water. The liquids weren't really confined. However, it was the very beginning of the use of water. Later on in history, we were able to use the power of water in order to do useful things. Some of the sawmills were water powered. You know, they had a mill that was run by a water wheel. Some other devices, but originally that was kind of the derivation of hydraulics, or where it kind of came from. The general terminology, when it's used in modern world, it explains the behavior of liquids, not just liquids that are flowing, but also statically contained in a vessel. And for aircraft usage, we're really talking about confined liquids, where we can transmit hydraulic fluid and create transmit force. So it says when we're talking for aircrafts anyway, what we're trying to do is we're trying to push hydraulic fluid into an actuator and make that actuator piston move. It says a science that explains the flow of confined liquids to transmit force in an aircraft. You'll notice that we've got groupings of hydraulic lines in many aircraft, and passing in those lines would be hydraulic fluid that is essentially pushing to an actuator in order to make an actuator move. And I'll show you a little video from Modern Marvels. We have a little bit of time tonight, but it explains a lot about the basics for hydraulics. But anyway, that's what we're talking about for hydraulic theory. This is important, even though it's not specifically for hydraulics. There are certain danger areas around aircraft. They show a turbojet aircraft here, or a turbo-powered aircraft, but we have similar hazards even with propeller-driven aircraft. And the big thing that we have to be worried about is the exhaust of the aircraft engine and also the intake area. If we're talking about a turbine engine aircraft, sometimes the exhaust area that we have to be concerned with is anywhere from about 200 to 350 feet. And you can see all sorts of YouTube videos where baggage parts have been overturned or pushed around as a result of getting too close to the exhaust of an aircraft. Then you've got a picture someplace of a baggage container that's been nearly ingested into an aircraft engine inlet. So again, you have to be kind of careful. Usually the minimum safe distance around the engine and inlet area is right around 25 feet at idle. So again, a lot of things can be ingested as the engine is running, and a spot for the engine will hurt it. And again, the exhaust blast is dangerous anywhere from about 200 to 350 feet when the engine is at takeoff power. When the aircraft is at idle power, the exhaust blast to the rear of the aircraft is somewhat substantial. Okay, so important. This is important as well for turbine engine aircraft. On many aircraft, they've got a red stripe, a radial line that is on the cowl of the aircraft engine or in other locations, and that indicates the turbine plane of rotation. If the turbine should burst during operation of the engine, you don't want to be in alignment with that red radial line, because you will be hit or possibly hurt by the explosive force of whatever's going to come out of that turbine that's bursting. So again, stand out of that area. You don't want to be there. Engine exhaust areas, again, the answer to an FAA test question will ask you, I've got it in red. Again, the exhaust areas at full power, anywhere from 200 to 350 feet is really the area you kind of want to avoid. Engine intake areas, always a foreign object damage area within a distance of about 25 feet or so. There's potential of swallowing something into the engine inlet. So again, kind of important. This is also important too, high intensity sound. When the decibel level gets to be right around 110 to 130, you risk permanent hearing damage. And this is no joke. And it's cumulative over time. Short exposure eventually builds to, for sustained periods, where it's cumulatively absorbed, it'll lead to permanent hearing damage. And I don't know that there's any recovery. I've got a Navy commander friend that is in serious health has serious health issues right now. He was exposed to C-130s for a long period of time. And again, in those days anyway, I don't know that they provided really great hearing protection, but he's got tinnitus, and now he's got a 25 hertz tone that will not go away, and it's maddening. So what I can tell you is guard your ears so that you don't have hearing damage or hearing loss. They're very, very damaging for the body. Operational radar exposure, possible eye damage, sterility, and cancer. Some aircraft, the radar beneath the radome is inhibited from operation by the squat switch on the landing gear. However, don't always count on that. So just be aware that if you're working in and around the aircraft and they have anything that in its radar waves, you can potentially absorb that, and it can cause severe health issues. Cancer, sterility, damage, possible eye damage, so watch out. Power actuated equipment. This is the big deal with hydraulics. It's uncaring and it doesn't I think that pretty much sums it up. It doesn't care. It doesn't care if you're a good person, bad person, whatever. If you put your arm or a leg in an area where an actuator is going to move, it develops a tremendous amount of force and from force multiplication. And you'll crush an arm, or you'll crush whatever's in the way. So be aware. Electrical, hydraulic, pneumatic are all capable of potential damage or potential injury. Injury and death. I mean, we can always replace an aircraft or replace a component, but there's nothing that we can do about the loss of life or loss of limb. So again, be careful. No-step areas on aircraft. You'll see that there's structural areas that you can walk on, or at least will support a load, not necessarily walk on. There's other areas that don't take very much to be damaged. So they're usually stenciled with some type of indication on them that says that there's a problem. They use the word no-step for that. So structural damage, when you push and pull on an aircraft, you kind of have to watch what you're doing too. If you look in the standard practice area of the aircraft manual, service manual, they usually give you some guidance on how the aircraft can be handled. Just realize that if you're working with a small general aviation aircraft, they're built out of aluminum alloys that are 25 and 30 thousandths thick in thickness for materials. It doesn't take much to damage them from a load. So again, you have to watch what you're doing. Servicing areas and bays. This is a potential FOD area where we have to service hydraulic fluid into a reservoir or maybe service an accumulator. They're usually relatively clean, but sometimes they're filled with, or at least littered with debris, safety wire, a lot of dirt. Sometimes the hydraulic fluid spills, it creates kind of a gummy mass that attracts further dirt and further debris. So this area should be really clean. And what I would recommend doing, if you use tools, always take a tool count. Make sure that you don't leave anything behind. Sometimes it's easy to do, but always a possible FOD area or FOD potential area. Hydraulic, electrical, and pneumatic power off unless it's required by the aircraft. Common sense. If you don't need to have the electricity on, you don't. In some cases you have to, but again, the service manual will tell you if you have to have electrical power applied or pneumatic power off or on, whatever the case may be. But use the service manual to see what procedures are required. Aircraft should be grounded, no smoking near the aircraft, common sense, most of the hydraulic fluids that we use for commercial aircraft are fire resistant, but why take a chance? So again, we prefer not to, induce anything that might happen. So no smoking, certainly around aircraft. And again, to guard against static discharge, the airplane should be grounded. Use only manufacturer's approved cleaning solvents for reasons of fire hazard or aircraft damage. There's a lot of coatings that are used on components that are damaged by commercial cleaners of unknown nature. So again, the manufacturer will specify what's to be used when and where, and don't make substitutions. You can easily damage components. You might even void a manufacturer's warranty by using the wrong kind of cleaning material. H-60 aircraft that's got the elastomeric rotor head, you put a little bit of WD coating on that elastomeric bearing. Same thing is true with a lot of the other rubber components. They're not tolerable Use care with compressed air and nitrogen. We use compressed air sometimes for servicing purposes, same thing with nitrogen. But I prefer not to use a shop air to clean anything off. When you're blowing debris, the debris ends up going someplace, so probably in the aircraft. So I prefer to use a vacuum if I can. And with nitrogen, it's probably the more preferred material or gas that we use for servicing. Accumulators that are serviced with nitrogen, there's a reason why. It helps to prevent an explosion. And the reason being is that nitrogen is pretty much an inert gas. It doesn't support combustion. On a lot of aircraft tires, large aircraft, we also inflate tires by virtue of an airway that is directed with nitrogen. When that rubber compound gets hot, we're trying to do everything we can to prevent an explosive environment. So the large aircraft tires are generally inflated with nitrogen. Know the location of fire extinguishers and their appropriate class of fire. So I think you all know from general class A, B, and C, right? Class A fire would be for fighting what type of fire? Paper, wood, pulp products. How about class B? Petroleum, fuel, that sort of thing. How about class C? Electrical. How about special class D? Metals. Very good. You know it. Clothing free of contaminants causes of illness and fire hazard. Oh boy, I can tell you a little bit about that. With some of the hydraulic fluids, they're flammable by nature, like millage 5606. The last thing you want to do is walk around with clothing saturated in this stuff, because you're a walking match, you know. So it's not a good practice to do it. In addition, there are some additives in hydraulic fluid that are hazardous to your health. They're great things for hydraulic fluid, but they're not great things for your body. They contain anti-wear additives. One of them is called TCP, tricresyl phosphate. It's an anti-wear additive. It's in most of the hydraulic fluids, but sustained exposure to that can cause paralysis. So again, you don't want to walk around because of the chemical constituents of the hydraulic fluid, and also some of the fluids are flammable too. In addition, some of the fluids, more than just a regular nuisance, in the case of some of the phosphate ester base fluids, they're an extreme skin irritant. They'll dry your skin tissue out significantly, and boy, it's painful to come in contact with it. Trade name of one of them is Hydral. You have to be very careful with that stuff. I don't like it. It's great for aircraft and great for fixed installations for hydraulics, but again, it's the last thing you want to get in your eyes, the last thing you want to get on your hands. Wash your hands after you handle any of these materials. You should be wearing gloves and safety glasses anyway. So with fluids especially, you don't want to come in contact directly with them. Same thing is true with a lot of other things. Turbine engine fuel, I don't like to put my hands in a fuel sump, and not a good thing, especially near the bottom. Sometimes when there's entrained with water or water at the bottom of the fuel cell, there's no tetralethal lead in turbine fuel, and that means that there's potential for a lot of microbial growth. So you can end up with a nasty infection by exposure to that, to the stuff that's at the bottom of a fuel cell. So again, be really careful with stuff. Flash points. There's temperatures at which there's enough vapor under pressure, or vapor pressure, that if a source of ignition is present, you've got a potential for an explosion. You notice down at the very bottom of the list, gasoline, just MoGas, it's got a flash point of -50. What that means is that there's enough vapor given off at a temperature of -50 that if a source of ignition is available, you can light it, the vapor can light itself off. So again, really dangerous. Occasionally you'll see people doing really stupid things. You'll read in the paper or see something on the internet where somebody has used gasoline as a cleaning agent, and or even worse, they were storing gasoline in their house and too close to a water heater, and man, the vapors ignited and the whole house blew up. So again, you have to be really careful. Gasoline is not an acceptable cleaning agent. I realized in the past during World War II, they did a lot of wacky stuff. You saw sometimes things like this. You look at some of the old service manuals and they'll say, oh man, we're going to use gasoline for cleaning. That was an expedient method during World War II in Africa, okay, but not in San Diego here, okay? So again, that's not an acceptable cleaning material. No way.
I mean, there's no more cleaning your air filters, but
Well, we do have something. We've got approved cleaners that have flash points that are a little bit higher than -50. So we use solder solvent quite frequently. It's still an approved solvent, but some of the things are, again, really dangerous because they flash off so quickly, or at least their flash points are so low. Let's talk about hydraulic systems, some of their advantages. One thing is you can say about hydraulics, they're lightweight compared to their mechanical counterparts. And so we save a lot in overall weight in a comparison of the two. One of the big things that we can do with hydraulics also is we can transmit force around corners and lines and all other places that you'd have extreme difficulty doing it with in mechanical systems. When you want to transmit force with mechanical components, you have to have a series of pulleys and bell cranks and push-pull rods in order to direct that source of force to a different location, pretty much along straight lines that have to make turns and bends. And the only way you can do that is with mechanical components to connect the things. With hydraulics, we can route a hydraulic line from one location to another through confined spaces and bring it to an actuator that's very remote from where we're at without too much difficulty. So from a manufacturing standpoint, it makes things a lot easier to do. It's very easy to install. Also for hydraulics, very simplified inspection. Either it works or it doesn't. And what I mean by that is with a lot of mechanical things, because of the interconnections and sometimes the timing of components, it makes things kind of difficult to inspect. For hydraulics, we're looking primarily for leaks in the components. We're looking for proper surfacing of components. There's enough fluid in the reservoir. We're looking to see if the fluid is dirty occasionally for inspection. We may check the operation of a hydraulic component for travel, but that's about it. The hydraulic fluid by nature, most of them, they have a lubricating quality. So they're self-lubricating. You don't really have to provide for any type of external lubrication in most cases, not all, but most. So very simple to inspect. Something else, minimum maintenance requirements, servicing reservoirs, accumulators, filters, fluid sampling. This would be a normal course of activity for hydraulic systems. You might have to replenish a reservoir if the fluid level gets low. You may have to replenish the gas charge in an accumulator if it's lost. You may have to replace a filter element if it's dirty. You may have to sample hydraulic fluid as part of an inspection process. That's about all. So not much. Efficiency. This is generally true. Hydraulic systems are almost 100% efficient. It's true that electrical systems can approach this, but not quite. The only aircraft that I'm aware of where maybe electrical power is really used in abundance would be the 787 aircraft. That one is almost all electric. But for the most part, aircraft are kind of limited in terms of what they can do electrically. It's kind of a feature that is held not in great abundance on most commercial airplanes. But you'll notice that most of the flight controls are hydraulically powered. You'll notice that landing gear extend and retract hydraulically. You'll notice that almost everything is hydraulic, but it's a better, more efficient system. So roughly 100% efficient when you're taking it with a negligible effect due to fluid friction. I added this in here, rapid start and stop. When we have hydraulic motors that give you rotary motion, as soon as you apply hydraulic pressure, man, that motor starts like right now, like a cooling fan. And the same thing is true. There's usually no coast down. Once you cut the hydraulic flow to it, the motor stops almost instantly. So this is because of the incompressibility feature of hydraulic fluid. Well, liquids are considered to be incompressible. You can't really change their volume by applying additional force to a confined liquid. So not true of gases. Gases are compressible, but hydraulic fluids are considered to be incompressible. System usage. What do we use hydraulics for in aircraft? Use it for actuation of primary flight controls, elevator and rudder. So elevator, rudder. We can also use hydraulics for secondary flight controls too. You can use it for flaps, slats, spoilers, speed brakes, anything that would be kind of ancillary in operation. You could use it for braking systems, independent and dependent brakes, emergency brakes, thrust reversers. I mean, it's almost limitless what we can use hydraulics for. But on small general aviation aircraft, sometimes the only thing that's really hydraulic would be the independent brake system, or maybe flaps in some cases. But you can see the advantage of it. If you can have a distribution network of hydraulics, you can bring hydraulic force and make it available to many things on the aircraft. So it makes things work much easier, especially primary flight control. A lot of mechanical advantage is required to overcome flight loads. So it kind of explains why it's used for that. Autopilot systems. Some autopilots are hydraulically driven anyway. They're electrically controlled, but they're hydraulically driven. Same thing with the yaw damper on some aircraft. And here's an example of inspection. Maybe one piece of equipment missing from that lady's eyes, but maybe some safety glasses. But you can see that inspection pretty much is relegated to looking for leaks, looking for correct routing, looking for chafing on lines, looking for maybe routing of electrical wiring that goes to some of the other components that are there. And she looks like she's got a cleaning cloth at the ready to clean up leaks. Pretty simple. Here are some components I happened to pick out. They were kind of interesting anyway. Hydraulics comes into play. Here's a picture of a U2 speed brake used on an aircraft. There's two of them. Landing gear actuators, usually they're featured on many large aircraft. Power control unit that's used for boosting hydraulic force to make an aileron move on a 747. We use a lot of acronyms in this area too. PCU stands for Power Control Unit. It's a self-contained actuator and positioning device that's commanded by usually an electronic control or an autopilot system in order to provide for positioning the aileron in this case. So it receives an input maybe from an autopilot or from direct control from the cockpit, from the cabin. Let's see if I've got something here for you. I don't know what this is. Some of these links don't work too well anymore. Yep, that one's gone. Let's try this one. Thrust reverser. Spoilers, ground spoilers.
The thrust reverser, that's just simply cutting off, or how's that? The thrust reverser, right? Does that? Yeah. It's just simply cutting off
It's converting the exhaust of the aircraft engine upward rather than toward the rear.
Yes,
Drilling is flat. Flaps. Probably done it in any cruise school. A lot of ports. So you can see some of the usage anyway. We also use it for starting systems on some airplanes. Most of the Sikorsky aircraft start hydraulically. There's a reason for that. In order to motor the aircraft engine, sometimes it's more efficient to do it hydraulically than electrically. And it's self-contained in many cases. A lot of the Sikorsky aircraft have accumulators where storage of hydraulic fluid is possible. we release that fluid into a hydraulic motor in order to start the APU for the aircraft, and then during start, the accumulator is recharged again. So that's how it should work. In the event that the accumulator becomes depleted, they sometimes have a hand pump aboard the aircraft. You can pump the accumulator back up again in order to push the, or have it push again down the fluid for restart. Some aircraft, they use it for utility systems. They've got a cargo door, a ramp, or a canopy. For a turboprop aircraft, they sometimes have a propeller brake that prevents the propeller from windmilling during shutdown, and so they'll use it for that. Some helicopters have a rotor brake that's hydraulically powered. Some specialized systems, some windshield wipers are hydraulic in aircraft. A lot of the Grumman military aircraft have hydraulic windshield wipers. A lot of the Sikorsky do too, the H-60 does. Wing fold on some aircraft, like the F-14, some of the others that are carrier-borne airplanes have wing fold capability. And radar antenna. In order to cause the sweep on the radar antenna, sometimes we've got the antenna itself is movable by a hydraulic motor. For identification purposes, you should realize that most things that carry some type of liquid or gaseous material are identified. There's a mill standard called Mill Standard 1247 that we use for identification purposes in aircraft. You can see down at the bottom over here we've got one particular one for hydraulic. For hydraulic systems, the way we've identified the lines is by a series of color-coded bands. We'll use a blue and yellow. The symbology that they use is always a black circle on a white background, and they've got the word hydraulic. So for people that can't speak English, for people that are colorblind, and for people that can only understand symbols, I guess we've provided three different methods of identification for those systems. The symbology, regardless of system, will always be a black symbol on a white background. That, by the way, is the answer to an FAA test question. So a black symbol on a white background. In the case of pneumatic systems, they've got what looks like a series of diamonds that are interconnected, black diamonds on a white background. They use a reddish and blue color code for pneumatic systems. You'll see there's other things too. For lubricating oil, they'll use interconnected rectangles, yellow for the color code for word lubrication. For fuel, they use diamonds. I don't know where it is over here, but
At the bottom.
yeah, okay, yeah. So they use diamonds. We use the word fuel in kind of a reddish brown color for it. But everything is generally identified by those three different methods of identification. And you take a look at some lines. This is just a black and white drawing. They'll provide additional information on the line. For example, it may have the color coding for pneumatic systems, but in addition to it, they may have what compound or what material is inside of there. In this case, it's compressed air. There may be a hazard code. This means physically dangerous in, and they give the specific pressure that would be encountered in maybe the direction of flow. So again, that might also be provided as well. Mill Standard 1247, it's not only used in aircraft, but it's used in a lot of equipment that are furnished under government contract, even land-based vehicles. So anything that is identified by this format is usually Mill Standard 1247, or color, language, and geometric symbol. And regarding those hazard identifiers, FLAM, you might guess what that means. That means flammable. Toxic means that it's poisonous. It's got the word toxic. AHM means it's either an anesthetic or a harmful material. It says all materials are productive of anesthetic vapors and or liquid chemicals and compounds hazardous to life and property, but not normally productive of gas dangerous quantities, or fumes or vapors are in this category. Physically dangerous, even pneumatic systems where you've got air, obviously that's somewhat of a pneumatic hazard. So you'll label this fighting. Okay. And here's some examples of some different materials that might have different coding. Air under pressure, physically dangerous. Alcohol, obviously flammable. Freon, physically dangerous. Gaseous O2, physically dangerous. Petroleum gas products, flammable. trichloroethylene, it's listed as AHM, okay, and anesthetic, I guess, in some cases. And a little bit about hydraulic systems. It looks overwhelming when you look at a picture like this. This is the landing gear, the nose gear area, I think, of a 737. But you can see here that if you look closely, they've got color-coded tapes that are at different locations, indicate that they're generally hydraulic. In addition to it, you'll see a lot of purple tags in aircraft too, near hydraulic components. That tells me something special too. It gives me a clue as to the type of hydraulic fluid that might be used. It's probably going to be a phosphate ester-based fluid, like Skydrol. So, again, it looks kind of overwhelming. The biggest asset in your toolbox would probably be time. And with a service manual, when you have to troubleshoot your service aircraft, because in here, it looks like everything is just a maze of spaghetti. So again, this is what I want you to remember. Color coding blue and yellow, symbology is going to be a black circle on a white background. And this is kind of important too. If you were to look in service manuals for aircraft, we have kind of a Dewey Decimal system of organization. It's called the Airline Transport Association Numbering System, ATA 100. If you go to any ATA 100 outline service manual, Chapter 29 will always be hydraulic systems. If there is no hydraulic system, there will be no Chapter 29. Also, too, the end use of those components, Chapter 27 will generally be flight controls, and landing gear will be Chapter 32. I'd like you to remember at least the number Chapter 29. So please remember that. Important. Here's a picture of a grouping of hydraulic lines, a run of them in a C-130 aircraft. And again, you can see that they've got the color-coded markers to identify what's what. They even have sometimes even directional arrows to indicate direction of flow. They might have check valves or orifice check valves installed in the line in order to allow flow in one direction only or restrict flow in one direction. But that's a grouping of nice picture.
It's really pretty.
This came from a Douglas aircraft, either I think a DC-8 or a DC-9. But again, there's a brake accumulator inside of an aircraft, a door latch assembly, and the reservoir servicing hand pump. Some aircraft, in order to fill the reservoir or replenish the reservoir quantity, well, they have an onboard hand pump that they put into a container of hydraulic fluid and they replenish the reservoir with it. So it's an onboard piece of equipment that is already there. Picture of I think this is also a DC-8 or a DC-9 aircraft. This is a filter module, and we've got usually pressure and return filters that are located in different in the same location that provides for servicing. Sometimes we have the outlet of a pump. You might have a filter on the pressure line. The return line that leads back to the reservoir will also have a filter, but it makes it kind of easy in order to be able to service both of the components at the same time, the filter elements. So they have everything incorporated into a filter module. We've got a couple of pressure or temperature transmitters that are installed in the line in this location that gives us an indication of fluid pressure and also temperature. And we've also probably got some differential pressure indicators mounted at the top of the filters, filter heads, and that gives us an indication if the element should be potentially contaminated. They're sometimes called telltale indicators or delta P indicators, and they're designed to respond to difference in pressure. When there's so much pressure on one side of the element, the filter element, versus the other, it trips or triggers the differential pressure indicator to indicate. So it alerts you that there's a potential problem with the filter. Another picture, 737, again, man, is you've got, you can see the nose gear, I'm sorry, you can see the nose gear in that picture. And again, a lot of the components are labeled, or at least identified as being hydraulic. These are reservoirs. One of them is, many of the Boeing aircraft, they have usually three independent hydraulic systems that work in unison in order to furnish hydraulic power. but they sometimes have the reservoirs that are sometimes co-located near them. So you might have system A, system B, and system C. Well, in this case, you might have one system A reservoir, you may have a system B reservoir located next to it. So that's what they have. Which is preferred, hydraulics or pneumatics? Well, you all know hydraulics deals with pushing confined liquids, and you know what pneumatics is. It's the use of compressed gases, or primarily air, but it could be almost any gas. There's no hard and fast rules, but however, I will tell you this. Speed, you'll need a medium amount of pressure, only a fairly accurate control, usually pneumatics, medium pressure, more accurate control, combination, high pressure or accurate control, usually hydraulic. After about an hour, get going. All right, I'll let you copy these, put down. ATA 100 for pneumatic systems, chapter 36. The end users, usually chapter 21 for air conditioning and pressurization. And engine air systems, this would be primarily for cross lead and starting, sometimes chapter 75. Remember the coding that I've given you. Usually they'll have a series of interlocking diamonds for pneumatic systems, and the color coding is going to be kind of an off red with a blue for pneumatics.
So like in air systems, if there were an ATA manual for like a Lansmouth AN2, you know, or a Yak, you know, obviously there's not a manual for those, but if there were, their starting system would probably be chapter 75.
It would be. Some of the newer Cessnas are ATA format, even for the small aircraft.
Really?
So, but not a lot of them. If you look at the more modern Cessnas that were manufactured let's say in the after year 2000, you might find some that are ATA outline, but the bulk of them are going to still be the traditional format. They won't be coming back. Anyway, that's what they got.
Interesting.
Okay. This shows you just a simplified view of a plumbing diagram for a large aircraft hydraulic system. You can see kind of what they do. You have to have a beginning point and an end point for hydraulic fluid flow. What they do is they deliver hydraulic fluid from a reservoir. And this might be for a large aircraft where they've got 3 independent hydraulic systems. So they've got maybe system A reservoir, a left, a center, and a right. And the hydraulic fluid is delivered into pumps. And a lot of Boeing aircraft, they have a combination of electrically driven pumps that they call ACMPs. These are alternating current motor pumps. They also have engine-driven pumps, EDPs, that they provide fluid to. The pumps really don't create pressure. The sole purpose of really any pump is just to provide flow. You'd have to trap that flow in order to create pressure. But a lot of folks just refer to the pump as the pressure producer, but it's not. It's just a method of creating flow. So we deliver flow from the pumps into the from the reservoir into the pump. The pump pushes that fluid in the hydraulic circuit. The lines that are indicated as red are pressure manifold lines to specific components. And again, if you trace out any of these lines, you see for reasons of safety and redundancy, sometimes we provide flow into the same component from 2 different sources, or we have an alternate source of pressure from a different hydraulic system. So that if one hydraulic system should fail for whatever reason, you have hydraulic power still available. So it's kind of interesting too when you look at kind of the hierarchy of the division, or at least the distribution of hydraulic fluid, how every different manufacturer is kind of done things. This would be kind of typical of a Boeing aircraft. You'll notice too that they've got what appears to be a couple of check valves here that go into the reservoirs. On many of the Boeing aircraft, they pressurize the aircraft with the reservoir with air, bleed air. It reduces it in pressure, and that provides the push on the hydraulic fluid to prevent cavitation of the pumps. So it'll do that. So you'll notice, again, a lot of those systems support not only an engine-driven pump, but also an alternating current motor pump for both left, right, and center. And also we have specialty pumps that we have aboard the aircraft. We have a specialty pump on a large commercial aircraft called a RAT. It stands for Ram Air Turbine. We'll talk about that much more in detail later in the class, but it's a air-driven, in many cases an air-driven pump. It can also be an air-driven generator in some cases for some aircraft. It's extended into the relative wind in the event of complete hydraulic failure, and it supplies essential hydraulics for the aircraft if everything is kind of gone out. In addition, on many aircraft, they have a device called a, does this have a PTU? I don't know if it has a PTU in it. I guess it doesn't. But they have a different pump that allows for taking fluid from one reservoir and routing it through a combination pump and motor in order to supply hydraulic flow. And it does it all without really stealing fluid from a particular system. It just attempts to repressurize a system that's lost its pressure. You'll notice also something too. We also have to be concerned with heat. In many large commercial aircraft, they have heat exchangers that are buried inside of the fuel cells of the aircraft. And they're radiator-like devices, but they're liquid-to-liquid heat exchangers. They use the fuel as a source of cooling for the hydraulic fluid that ultimately is going to pass back into the reservoir. So sometimes the reservoir is buried in such a location that it just can't cool properly, or at least it's not supplied with enough cooling ability. So the return fluid in many cases has to go back into the reservoir. It's been cooled by the coldness of the fuel in the fuel cell. You know, even when no hydraulic system is being used, the discharge of the pumps in some cases is provided with a case drain that goes back into the reservoir to provide kind of a natural cooling loop. So that's what they've done with that. Anything else? I think that's about it. So anyway, this is what we look at for kind of a large aircraft for a typical system. And this is one from a 757 aircraft showing the complete system. Again, left, center, and right, and again, simplified. And it shows you that, for example, on spoilers, you've got several different inputs that all provide hydraulic power. And if one system is lost, well, you still can operate spoilers, ailerons, or thrust reversers. And so it works pretty well. Here's that power transfer unit that I was kind of looking for here. The power transfer unit is used in a lot of large aircraft in order to power a system that maybe lost hydraulic pressure from who knows what, maybe a loss of fluid. But it does it without direct transfer of hydraulic fluid. The PTU is essentially a pump and a motor in a common housing. So some of them are reversible. It'll work as either direction as a pump or a motor. But if, say, for example, the left system has lost its pressure, what we can then do is introduce fluid into the motor side of the PTU. It uses hydraulic fluid from, I have to trace this back, but it looks like from the right system, in order to repressurize the system by operating the pump on the left side. So there's no direct transfer of hydraulic fluid. After all, if you've lost the fluid from the left side, this is your opportunity to attempt to repressurize the circuit using existing fluid. And it usually picks up fluid from below the standpipe level, the very bottom of the reservoir that's held in reserve. So it's good for a limited period of time. Compare that with maybe something like this. That's a picture from a B-24 aircraft, a Liberator from World War II. Just a few things were operable hydraulically in that aircraft. I think the brake system was, and I think that maybe landing gear and maybe a couple of things in it, but not too much. And so it's a very simplified system. They've got an accumulator in the circuit. They've got a few other things, maybe a pressure regulator. I don't think they even use variable displacement pumps on the very much simplified. As a matter of fact, I think they only have one engine-driven hydraulic pump in the aircraft. And if you read the starting sequence for the B-24, they have to start engine number 3 first, if I remember right. And the reason that they do that is because the hydraulic pump that's engine-driven is on engine number 3. So without that started first, they really have no push of hydraulic fluid in order to make the other components work. So that's why number 3 engine is kind of the critical one to start first. Okay, so that's what I can give you for a moment on hydraulics. What time is it now? 5:50. It's close to 6. Why don't you come back here at 6:30, and then I'll show you a little bit of a movie of modern marbles. So we'll see you back at 6:30.